Welcome to our Quantum Deep Dive. Today, we're jumping into one of the most fundamental and, frankly, one of the strangest ideas in all of physics. Our guide for this is Jörg Owe Schneepot's brilliant essay, Interference and Diffraction. And we're going to get right to the heart of what makes the quantum world so weird and so incredibly powerful.
So, let's start with this quote, because it really just throws you into the deep end. Each electron interferes with itself. I mean, what does that even mean? It sounds completely impossible, right? Like saying a single bowling ball knocked itself over. This is the mystery we're going to unpack today. And trust me, the answer is even stranger than the question.
All right, so to really get our heads around this quantum weirdness, we actually have to take a step back. We need to look at the world we think we know, the classical world, and talk about how waves are supposed to behave.
This story really gets going all the way back in 1678. Christian Huygens comes up with this idea that a wave is made of countless little wavelets all moving together. It was a really neat theory, but the real knockout punch came in 1801 with Thomas Young's now famous double-slit experiment.
So what did Young see? Well, he took a beam of light and aimed it at a wall with two tiny slits in it. Now, if light was just a stream of particles, like little bullets, you'd just expect to see two bright lines on the screen behind them. But nope, that is not what he saw at all. He saw this beautiful, complex pattern of many bright and dark stripes.
And what he was seeing is a classic wave phenomenon called interference. As the waves of light pass through both slits, they spread out and start to overlap. Where the peaks of two waves meet, they add up and get brighter. That's constructive interference. But where a peak meets a valley, they completely cancel each other out, leaving a dark spot. That's destructive interference. It all makes perfect logical sense for a wave.
And for over 100 years, that was pretty much the story. Light is a wave. Things like pebbles are particles. Case closed. But then, the quantum revolution showed up and basically flipped the entire table over.
The big twist came in 1924 from a guy named Louis de Broglie. He asked a truly wild question. What if it's not just light? What if everything, every particle, every single electron also behaves like a wave? He suggested that all matter has a wavelength. It was a completely radical idea, and it set the stage for a whole new way of looking at reality. And this really frames the big conflict. In one corner, you've got our everyday classical particles. Think of a baseball. You throw it, it follows one path. It can't be in two places at once. Simple. But in the other corner, de Broglie is saying quantum particles are different. They live a double life. They can be a particle, sure, but they can also be a wave, existing in this weird state of all possibilities at once, called the superposition.
So, how in the world do you even begin to test an idea that sounds so crazy? Well, you go right back to the scene of the crime, the double-slit experiment. But this time, you do it with a quantum twist. You fire single electrons.
Okay, so first, let's just reset our expectations. Imagine we're shooting tiny paintballs at those two slits. What do you expect to see on the wall behind them? Right, two lines of paint. Each paintball goes through one slit or the other. It's totally simple, totally predictable.
And, as we already covered, if you send a classic wave through those same slits, you get that classic interference pattern. So particles give you two lines, waves give you a bunch of stripes. Got it. But what about electrons? Are they particles or waves?
And here it is. This is the experiment that completely shattered physics. Scientists fired electrons, one at a time. This is so important. There's no way for the electrons to bounce off each other or interact. Each one makes its journey alone. It hits the screen, blip, one little dot, then another, and another. But as you watch thousands of these single dots build up, what pattern do you see? An interference pattern, the exact pattern a wave makes.
I mean, just let that sink in for a second. A single particle, all by itself, behaves as if it went through both slits at the same time, interfered with itself, and then landed on the screen in just the right spot to help build a wave pattern. How is that even remotely possible?
Well, the answer is a concept that is central to all of quantum mechanics, the wave function. You see, the electron isn't a little physical wave spreading out. Instead, it's described by this abstract mathematical wave of probability. This wave function represents all the possible places the electron could be. So when that probability wave hits the two slits, it goes through both, interferes with itself, and that interference pattern tells the actual particle where it's most likely to land. And just when you think your brain can't handle any more weirdness, it gets weirder. Because the next obvious question is, okay, but which slit did it really go through? So physicists tried to find out, and what they discovered was just mind-blowing.
So check this out. We run the experiment again. No detectors, just firing electrons. And sure enough, the wave-like interference pattern builds up. But now let's put a tiny little detector by the slits, just to peek and see which one the electron goes through. The very instant we do that, the instant we look, the interference pattern vanishes. It's gone. And all we're left with are two simple bands, exactly like the paintballs. The electron suddenly starts acting like a particle.
And let's be really clear about this. This isn't because the detector is clumsy and knocks the electron off course. It's much more fundamental than that. The simple act of knowing which path the electron took, of gaining that which path information, forces its wave of possibilities to collapse into one single, definite reality. At the quantum level, the universe seems to change depending on whether or not we're watching it.
Okay, so this is all incredibly fascinating, but you might be thinking, all right, does any of this bizarre stuff actually matter in the real world? And the answer is a huge, resounding yes. This isn't just a weird quirk of nature. It's the engine for a whole new technological revolution. Today, scientists and engineers aren't just confused by this weirdness, they're actively using it. Quantum computers, for example, work by carefully controlling the interference of their qubits, making the right answers build on each other constructively while the wrong answers cancel themselves out. From the unbelievable precision of atomic clocks to unhackable quantum communication networks, harnessing interference is literally how we're building the future.
And that really is the biggest takeaway here. For so long, the strangeness of quantum mechanics felt like a bug, a problem in our understanding of how the universe works. But we now realize it's not a bug at all. It's a feature, an incredibly powerful feature that we can actually build with. Which of course brings us back to that one final, absolutely massive question that physicists and philosophers are still wrestling with today. If reality fundamentally changes when we measure it, what is it like when nobody is looking?
Our journey through this wild and wonderful concept was made possible by the fantastic essay Interference and Diffraction, written by Jorg O. Schneppet. It really helped us map out this incredible territory.
Thanks so much for joining us on this explainer. And hey, if you want to go even deeper down this rabbit hole, we really recommend you visit schneppet.de. Until next time, stay curious.
Schneppet.de is a private project by Jorg O. Schneppet dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.